All right, so this is lesson number 37, parametric situations, which is a continuation of last week. We did graphing parametrics, if you remember, and we did converting from rectangular form to rectangular form from parametrics equations. So today we're looking at word problems for that. All right. So here's where we're at in the calendar. Since we didn't have class yesterday, we're just going to do these two lessons as one here. It's fine. It's just it's not going to be that much added time. Maybe like 10-15 minutes. We'll do an extra problem. If you need to go early, that's fine. But we'll do the parametric situations today, and then we'll be done with that unit of parametrics, and then we'll move on to our last unit, which is on polar. And so that's a 2-lesson unit, polar points and polar equations, okay? And then Friday, Zoom office hours, and then the next 2 weeks you have AP exams, and we'll do review during that time. I sent a message on Remind about ACP testing, so there is no ACP district testing. There's also no teacher-made ACP testing, and so for E2 on that grade, that's usually 15% of your semester grade, that category will just be blank, and your grade will be average as an average of the 4th, 5th, and 6 weeks. So that's the update on that. So I won't be assigning any work during these days. That can, I guess, be a catch up if you really have any other missing assignments. But that's just an update on that. So any questions with respect to calendar stuff before we get started into the lesson? Say that again. Oh, I think Justin, I think you might have your video unmuted, or your video, yeah, your sound off mute. I think someone in the background said something. But any questions on any of that? Calendar, where we're headed? No? All right, we'll go ahead and get started then. As always, we see our 4 goals. We will learn math, build character, never give up, and ask why. All right, let's jump into it. So if you remember last week, we started the parametric unit by me showing you this problem and saying this is the problem we'll be able to solve by the end of class, and we'll do that now. So I'll reread it. It says a baseball player hits the ball at a 28-degree angle with an initial velocity of 103 feet per second. The bat is 4 feet from the ground at the time of impact. Assuming that the ball is not caught, determine the distance traveled by the ball. So what we have here is there's a number of factors we have to consider. We have the ball that is being hit. The initial velocity is 103 feet per second. So its speed is 103 feet per second. The angle is 28 degrees. And he hits it starting at a height of 4 feet. All of that matters. The ball, we know gravity will pull this ball down. We have to consider gravity, and eventually it's going to hit the ground somewhere. And we're trying to find the distance traveled from here to here. What is that distance? Before, we didn't have enough information to solve that. We know about quadratics, but based on just this, it's not enough information to write the equation of a quadratic. We would use parametrics here to figure out how far the ball traveled. So we'll get to this, but we're going to work our way up in understanding the different parts of this problem to where we will be able to figure out how far the ball has traveled, okay? So we're going to work our way up. I'm going to kind of explain some concepts we need to know first. So a couple things to remember is that speed is equal to distance divided by time, right? For example, when you talk about speed, you might say 5 miles per hour. So that's 5, and then it's miles per hour. The miles is the distance, right? The hours is the time. When you talk about speed, it's always a distance over time. Speed is a change in distance over time. If you do some simple algebra there, and you multiply by time, then distance equals time times speed. So distance equals speed times time, all right? And so you would use that if I said, for example, you're driving at 50 miles per hour and it takes you 3 hours to get to Houston. And you were asked, how far did you drive? if you're driving 50 miles per hour, that is your speed. If it takes you 3 hours, that's the amount of time. So if you multiply 50 miles per hour times 3 hours, it gives you your distance, which would be 150 miles, right? Or if you just think about it intuitively, 50 miles every hour. So in the first hour, you drove 50 miles. Second hour, you drove 100 miles. Third hour, you drove 150 miles. So distance equals speed times time. That's important to note, that distance equals speed times time. We're going to come to that, okay? Velocity, we're kind of going through some recap here. Velocity is the speed of something in a given direction. So when we include a direction component, then it becomes velocity. So in this case, it says this is a velocity of 103 feet per second because 103 feet per second is a speed, but then it's a velocity because you have the angle measurement of 28, which includes that component of direction. So therefore, it's a velocity. So you can have 10 miles per hour north is velocity because there's a direction component, right? And we talked a lot about that with vectors. Acceleration, we haven't talked about, but you should kind of be familiar with it, is how fast velocity is changing. So if something is accelerating, like if you think about a car accelerating, it is increasing in its speed and increasing in its velocity over time, right? You're going faster or you're going, and so when you're talking about acceleration, it is how much the velocity is changing per time. So for example, you could say 5 meters per second squared, which means you're increasing 5 meters every second, that speed or that velocity, every second. That's why seconds squared. Every second you're increasing by 5 meters per second the speed, okay? So we're going to talk more about acceleration there. All right, so that's just definitionally. Is that a word? Definitionally. Definitionally. Oh no. All right. Any questions there? Okay. So when we talk about parametrics with a ball being hit, like the problem we looked at, it's going to be the section in your formula sheet that talks about projectile motion. Okay. And this is still parametrics. We're not going to be looking at free fall motion. Free fall motion would be like if you were here and you just dropped the ball from a height and it went straight down. That would be free fall motion, just straight down. It's not hit in a particular direction, okay? We're not looking at that for this problem because we're hitting something away, okay? So we're going to be looking at this equation here, vertical position and horizontal distance. Because we have two equations, that makes it parametric, because if you notice, we have a y equals and an x equals, and both of those are with respect to t. So t is our parameter of time. So these are parametric equations. Then you got some other stuff in there. So the one on the left shows you the vertical, how high the ball is at a given time. The one on the right tells you how far horizontally the ball is at a given time. And this here is telling you the acceleration due to gravity, which we'll talk about in a little bit. Okay, so that's the formula we're using. So let's kind of start this problem by thinking about if there was no gravity. So if this person was on the moon, there was no gravity, then when this ball is hit, what would happen to the ball if there was no gravity? And there was nothing in the way of the ball. That's a question. Sorry?
Would it keep going up?
Yes, it would keep going up. It wouldn't slant at all, wouldn't curve down, right? This would go directly straight forever until it hits something or until it gets to a planet that has gravity or something like that, right? So that's if there was no gravity. Now, let me give you 1 second. Okay. Now, let's just start with the assumption of just thinking about it from the perspective of the components of that without including gravity. Okay, so we're saying assuming that the ball would just keep going straight. Okay, so if let's look at this case of this ball and the ground being hit like a golf ball. Okay, so what we're going to look at is we're going to look at the horizontal and the vertical components of this particular ball being hit. All right, so we're going to call the horizontal component x. And we're going to say the y is the vertical component of velocity. Okay. And so let's solve for the relationship between v is representing our initial velocity of this ball being hit. So in the case of the baseball is 103 feet per second. Here we're just saying v, okay, just show the relationship. Oops, sorry. So in this case, we would do, we're looking just as x, so we're going to say cosine of theta equals x over v, because cosine is what is going to show us the relationship between x and v, because this is adjacent, this is hypotenuse to the angle. So the relationship between the horizontal component of velocity, this is vectors now, right? We talked about this. So the relationship between the horizontal component of velocity and the velocity and the angle is cosine of the angle equals x over v. Now, if we solve for x, we will multiply by v. So x equals v times cosine of theta. Okay, so this is the horizontal component of velocity. Oh no, I need this. Okay. Then we have y. Let's look at the relationship between y and v. We would use sine because this is opposite. So sine of the angle equals y over v. If we solve for y multiplied by v, this would be the vertical component of velocity. Okay, so we're just looking at right now if there was no gravity, the relationship between the horizontal and the vertical component of velocity. Okay, now remember, velocity is just speed in a given direction, right? So in this particular case, if we think about the equation, the relationship here, distance, we said, is speed times time, right? Distance is speed times time. And so if we think about this as our speed, this is just represented in variables. This is the horizontal kind of component of our velocity, which would be our speed, kind of, if you want to think about in the horizontal direction. If distance equals speed times time, and this is showing us speed, if you want to know how far the ball has traveled horizontally, distance, it would be that times time. So it would be distance, if we're saying is x now, x would equal, so if we're saying distance is x would equal our speed, which we're saying is v times cosine of theta, times time, which we don't know, which we'll say is t. Okay? This is going to be the general formula we'll use for the horizontal distance of how far the ball has traveled horizontally. I'm kind of trying to give you the explanation of why the formula is the way it is. So if you see here for projectile motion under horizontal distance, you see it says x, which is represented by horizontal distance, equals t, which is this t right here, we just have it at the end, times VO, which is the initial velocity, which is this, times cosine of theta, which is that. So that's where that's coming from. That's why it's distance is speed times time. That's why the formula is that. Okay. Now for y, this would then tell you, if we use the same principal, and that's speed. That times time would tell you how high the ball is, because that's distance. Now, if you look at this formula, however, there's a lot more to it. So we're going to look at that later. But if you just look solely at the height of the ball, it would be v times sine of theta times t. That is this portion of the formula. Okay? So that's where that's coming from. Let me pause. It's kind of talked about a lot there, theoretically without numbers. Any questions thus far? Did I lose any more? Is that there is gravity, right? So that was assuming there was no gravity. If there was no gravity and the ball was hit from the ground, then you would simply use these two equations here to determine the horizontal distance and the vertical distance of where the ball is, okay? But because there is gravity, the ball is being pulled down. So gravity being pulling something down only affects the vertical distance. It doesn't affect the horizontal distance, right? So that is why this remains the same. Horizontally, how far the bar has traveled is not affected by gravity. That would be affected by air resistance, which we're not including. That's a whole nother thing. So we're assuming no air resistance here for this. Air resistance would affect the horizontal distance, but we're assuming there is no air resistance, okay? Gravity would solely affect the vertical position because gravity is pulling something down. So if we think about the formula we just learned, we had this portion of it, okay? Now, the other part of it is coming from gravity. So this part right here, this subtraction is minus because that's going to pull the height down. If it was adding, it would make it go higher. So this part is accounting gravity. So minus 1/2 times g. G is acceleration due to gravity, okay? So we have these two values here. That's depending on whether it's feet or meters. So if the problem you're working with is in feet, then you would use 32 feet per second squared. So that means that in the Earth, so if you, I just did a quick Google search. So on the Earth, gravity's acceleration due to gravity in meters is 9.8 meters per second squared. On other planets, it's different. Okay, there's different gravity, acceleration due to gravity. So we're just always assuming we're on Earth, obviously. So acceleration due to gravity here is 32 feet per second squared and 9.8 meters per second squared. And use those interchangeably depending on what unit you're working with, okay? So that will be what your G is, okay? So on the Earth, as objects fall, they fall faster as they drop. We actually talked about that when we watched that documentary. I don't know if y'all remember. It's talking about Galileos and stuff, okay? Now this HO is being added. Whenever you see sub-zero, that almost always means initial. So this is talking about the initial height. So the initial height, you may or may not have that. So in this case, the initial height is 0 because it starts on the ground. So you wouldn't have this, it would be 0. But if this is starting up, then everything is moved up. So then it would be hit like that. So then whatever this height is, like if this height is 3, this would be 3. So that's all the components of determining the vertical position, okay? So that's where those two formulas come from. So when we're using projectile motion, we're talking about something being hit at a given direction. You have the velocity, gravity is in play. To determine how high the ball is, we would use this parametric equation. To determine how far the ball has traveled, you use this parametric equation. So that's where they're coming from. We're going to apply them now in a minute, but I want to make sure we're good with where they come from first. So any questions thus far? See one thumbs up. Hopefully we're all still awake. Okay. All right. I just want to first just start with the formula, and then we're actually going to get to that problem with the baseball. So just to make sure we know how to use that formula with what information we're given. So I'll just do this one real quick. So it says, suppose a ball is thrown 6 feet above the ground with an initial velocity of 75 feet per second at an angle of 25 degrees. What are the horizontal and vertical equations of the ball being thrown? We'll look at the second part of the question for later. So let's just say you wanted to write the equations of the ball being thrown. Let's start with the horizontal. Horizontal, we're using this. That's showing you a horizontal distance of the ball. So it would be x equals t, we don't know t, that's time, times VO, which is initial velocity, which in this case, the initial velocity is 75, times cosine of theta, which in this case, that is 25. When I write these equations, I always like to simplify what can be simplified. So like this whole thing, I would simplify in the calculator. What's that? 75 cosine of 25. So 67.97. So x equals 69.97 t. That's how I would write it, simplified. So that is showing you, based on this information, if you wanted to find how far the ball has traveled horizontally at a given time, you would plug it into that for t, and it would tell you that information. Okay. For the vertical, that's where we're using this longer equation. So it'd be y equals t times our initial velocity, that's what that represents, which our initial velocity is 75, minus, for parentheses here, 1/2. Now we have, oh, I'm sorry, I missed something. I missed the 75 times sine of theta. So that's sine of 25. I'm running out of space here. Minus 1/2. Then we have g, and that's where you have to determine which one you're using. So because this problem is in feet, which you can see from the velocities feet per second, we're going to use this 32. So 1/2 times 32 t squared, and HO being the initial height, which the initial height of this is 6 feet. So plus 6. And then I would just simplify this. So I would simplify what could be simplified. Oh, thank you, Claudia. She corrected me. I think I rewrote this on the left wrong. 60, this was 67.07. Did I type it in wrong here? Wait, why is it 67.0? Is this in radians, maybe? Hey, Claudia, you said the x is 67.07? 67.97? What did I write? Oh, okay. 67.97, my bad. I wrote 69. Okay. It's hard to flip back and forth and remember all the numbers. Okay. So then this part right here, we would simplify what we can simplify. So 75 times sine of 25. $31.69. We write this y equals 31.69 t. I'm gonna write the variable at the end. Minus, I can go ahead and do this math because that's just 1/2 times 32. That's minus 16t squared plus 6. Okay. I like to write it in standard quadratic form, so I like to write negative 16t squared plus 31.69t plus 6, just kind of because that's what we're used to writing it in a standard form there. So that would be the equations for, this should have a t on it. These would be the equations for parametric equations for finding out where the ball is horizontally or vertically at a given time. So if it question asks where's the ball horizontally and vertically after 0.9 seconds, you could plug 0.9 in here for t, here, and here, and that will give you the height. Okay. All right, let's look at that problem now. And we're going to solve this. So we should be able to do this based on the information we have now. So I'll reread it to kind of remind us what the problem is asking. So a baseball player hits the ball at a 28-degree angle with an initial velocity of 103 feet per second. The bat is 4 feet from the ground at the time of impact. Assuming the ball is not caught, determine the distance traveled by the ball. So what we're trying to find is, eventually this ball is going to be hit, and it's going to go down, and we're going to be trying to find the distance from here to here. What is that distance is what we're looking at. Okay, how far did it travel? So thinking about that, which equation would we be using to help us find that? Ideas? We're not using this because it's not free fall. Which equation will we be using to help us determine the distance traveled by the ball?
Horizontal distance equation.
Yeah, horizontal distance, because we're not trying to find out how high it is right now. We're just trying to find how far it traveled. So we're going to use this equation here. So x equals t, we don't know time. Initial velocity, VO, initial velocity is 103 times cosine of theta, which is 28. And we're going to put 103 cosine of 28. 90.94. This is our equation for horizontal distance. So what we're trying to find is x, right? We're trying to find x in this equation. But we actually don't have enough information right now because we need to know how much time it took, t representing time, for the ball to get over here. And then we can plug that t in here to determine what the horizontal distance is, right? But we don't know, it hasn't told us how much time it took for the ball to get there. So how could we go about finding how much time it took for the ball to get over here on the ground? I want you to think about that.
Position equation and then equals the two equations to each other and solve for t.
So set up the vertical position equation, and then you said set them equal to each other. So let's try that. So let's work with what she said. I think that was Natalia who said that. So y equals, let me do it in a different color. Y equals t initial velocity, VO, I don't know if y'all can see, it's pretty small, VO, initial velocity, which is 103, times sine of theta, which is 28, minus 1/2 times g. Now we're working in feet per second, so we're using 32. T squared plus HO, initial height. Our initial height here is 4. So we need to simplify that. 103 times sine of 28. That's 48.35. Minus 1/2 times 32, 16, plus 4. I'm just going to rewrite that in standard form. So I'm going to put the t squared first. Okay, so Natalia's right. We are going to use this equation somehow. However, we can't set them equal to each other because this is a y right here and this is an x. So they're different variables. So we can't use substitution and substitute the y in for x. But we are going to need to use this. So let's work based off of what she said. Other ideas to continue this. We have now, this equation shows us how high the ball is at a particular time. And what we need to know is we're trying to find this horizontal distance. We're trying to find the horizontal distance when the ball is on the ground. But in order to know the horizontal distance when the ball is on the ground, we need how much time it took for the ball to get on the ground. So we're trying to use this equation somehow to determine how much time it took for the ball to get on the ground. So that's where we're at right now. What can we do next?
You can substitute y into 0 because it has to hit the ground, so the height will be 0.
Okay, good. So at this place where the ball is on the ground, it is at the height of 0. So we can plug 0 for y and solve for t, right? And that will give us the time it took. That's important to note. So we're trying to repeat that. We're trying to find where the ball, what the time of the ball is when the ball is on the ground, because then that would help us to find the horizontal distance. The ball is on the ground when the height is 0. Height vertically is represented by y, so therefore we can plug 0 in for y. So it'd be 0 equals negative 16 t squared plus 48.35 t plus 4. And then we would want to solve for t. Now, usually when we solve a quadratic for t, we would factor, right? However, this has a decimal in it, and it's going to be hard to factor this because then we'd be working with a lot of decimals there. So there's another way we have to solve this here. So what's another way we can solve the quadratic for t? There's a couple ways. How can we solve for t to figure out what works? Nope. Other ways to solve for t. Amanda, what do you think?
Could we graph it?
Yes. Okay. Graph. Good. Jared, what you got is another way. Actually, there's 3 ways. Jared? Maybe he stepped out. Kevin?
Quadratic formula.
Okay, good. Why y'all staying quiet if you know the answer? Quadratic formula. Good. So we can graph. We can use the quadratic formula, which is negative b plus or minus square root b squared minus 4ac over 2a, right? We can use this as a, b, and c and plug it into that. Third way. Claudia?
They can't factor.
You can't factor, no. Well, it doesn't work. Well, it would be very hard because there's decimals. Is there a way in the calculator other than graphing?
And solve.
NSolve wouldn't work because it's quadratic. And a quadratic would only give you one. NSolve only gives you one answer, but it's similar to NSolve. If y'all remember menu, there's a menu 332, the polyroots. I showed you that a while back. So those would be the 3 ways. Let's do graphing because that's the most accessible. So actually quadratic formula would be the most accessible if you don't have a calculator. But I don't want to run out of space, so let's just graph. Someone read it to me, please, so I don't have to flip back and forth.
Negative 16 t squared.
And we would use x here if you're using Inspire.
Plus 48.35x plus 4.
Okay. So this is a graph. Now take note that this is not the graph of the path of the ball. This is the graph of the vertical distance of the ball with respect to time. That's important to note. This is not the graph of the path of the ball because y represents vertical height or position. X in this case, which is t, represents time. So this is showing as time is passing, how high is the ball. That's just important to know. Okay, so I'm going to go to trace, and I'm going to go over here. So this is where it hits the ground. 3.1 t, again, x represents t, which is time. So 3.1 seconds. So t is 3.1 seconds. That's how long it takes for the ball to hit the ground. So then now that we know that time, we can plug that in over here. X equals 90.94 times 3.1, and that will tell us 90.94, 90.94, 90.94 times 3.1, 281.9 feet. That would be how far the ball has traveled. So that is how we can use parametrics to solve this problem. I think that's pretty cool. Just by knowing the height of the batter when he hits it, and knowing the initial speed and the angle the ball is hit, we can determine how far the ball will go. That's pretty cool there. Any questions? All right, let's talk about these bottom two questions, and then I'm going to give you one to try on your own, okay? We're just doing one example here. I'm going to erase this. We're going to need some space, so I'm going to erase this as well. I'm just going to keep the equations. Excuse me. Whoa. Okay. So those are the equations we need. That's not going to change. We're still working with the same graph here. Okay, so part B. Is the ball going to go over the home run fence that is 250 feet away from the batter if the wall is 10 feet tall? So it would help to draw a picture here. So we're still working with the same ball being hit. We know that this took, what was that again? 200 and, what was that distance? Come on, help me out. I erased it.
281.9.
Thank you. So if there's a home run fence that is 250 feet, and it is 10 feet tall, now notice when I drew my yellow, that was just an estimation. That's not necessarily the exact direction. The question is, would it go over that? So if you think about it, this yellow, it could go like this, right? And then if there was no wall, it could land over there, or it could go over it and then hit over there. So we need to know whether it is going to go over it, whether it is going to hit it. So option A would say yes, it goes over, right? Option B would be no, it will fall short and it will hit the wall. Option C would be no, it will fall short and it will hit the ground. Which one can we cross out? For
C.
sure. We can cross out C, right? Because we know it's not going to fall short and hit the ground because we know it hits the ground over here at 280 feet. And the wall is 250 feet away. So it can't be C. It's either going to hit the wall or it's going to go over. So what we can do here is we can use the distance, the amount of feet that it is away, and we can plug that in for X because that's horizontal distance, okay? So it's going to be 250 equals 90.94 T. Let me change the color. I'm not sure if y'all can see that color. 250 equals 90.94 T because 250 is horizontal distance. And we're going to solve for T. That's going to tell us how much time it takes for the ball to get 250 feet away. So we're going to divide by 90.94. 250 divided by 90.94. Use my phone calculator. 250 divided by 90.94. So T would be 2.75 seconds. So it takes 2.75 seconds for the ball to get 250 feet away. So we can use that to then determine, okay, how high was the ball after that time by plugging it into the y equation. So then we're going to put y equals negative 16 times 2.75 squared plus 48.35 times 2.75 plus 4. That will tell us how high was the ball when it was 250 feet away. I'm going to have to use this. Let me give y'all a minute to write that down. I'm going to ask one of y'all to read that for me. Okay, can someone read that for me? So I can type it in here.
Negative 16, 2.75 squared plus 48.35 times 2.75 plus 4.
Thank you. Okay, 15.96 feet. So what would this mean?
The height,
The height. And so therefore, what do we know about the ball? Would it go over or would it hit the wall?
over.
Yeah, we'll go over it because the height of the fence is 10. And so it's somewhere up here at 15. So it went over it. Here it's at 15 and then it went down. So the answer would be A, it went over. Okay. Very good. If it was to fall short and hit the wall, what would this value have to equal? There would be a range of values it would have to equal. What would be the range of values that would have to equal if it fell short and it hit the wall?
It has to be less than 10.
It has to be less than 10 and greater than what?
0.
Okay, good. Less than 10 and greater than 0. If it's A, it has to be greater than 10. What about if it fell short and it hit the ground? Then what would this number have to equal? So if it hit the ground before the wall, what would the value of y be when you plug in order for the answer to be C? So if it went over, it would have to be greater than 10. If it hit the wall, it has to be between 0 and 10. If it fell short and say it hit the ground like somewhere over here, what would the value be when you did the math that we just did at 250 feet away? What would it have to be?
Is it 0?
Wouldn't be 0.
A negative number?
It would be a negative number. So it would be 0 in real life, in the sense that like this ball it wouldn't go underground, right? Like it would just roll. It would roll, and then it would still be at 0. But because we written the equation of a parabola, now if we're assuming like it continued, it would be going underground, and then it would be less than 0. So mathematically, when we plug in the value, it would be less than 0, but we have to think about the real life application as well. So in order for it to be, this would be less than 0. So if you get a negative number, you know, okay, it hit 0 before the wall. Okay. Very good. So see how many seconds it take. We already got that. That was this 2.75. All right. So this is kind of cool. This is just kind of the applications of how you could apply a parametric situation in solving a problem. So I think it's pretty neat. All right. Let me give you some time. This is the last problem we'll do. I want you to actually try this problem yourself. So I'm gonna pause and mute myself and give you some time to work on that, and you can send a message in the chat when you're done. Okay, just to make sure you understand the concept. Okay. Start down. Maybe the rest of us are still working. We can kind of work through it and see what we got. So Tammy, can you help us with setting up the first two equations?
Okay, so for the vertical equation, I did t times 40 times the sine of 30 minus 1/2, and then multiplied by 32 times t squared. And then there's no like initial height because it's 0. And then that's simplified to 20t minus 16t.
You said,
yeah, 16t squared.
wait,
So 20t, yeah, minus 16t squared.
Okay.
And then for the horizontal, I put t times 40 times cosine of 30, which simplified to x equals 34.64t.
Okay. Are we good with that? Do y'all agree with what Suchanvi said there? Or any questions up to that point? Yeah, see some thumbs up. Cool. Thank you. All right. Let's do Carla. Could you help us out with the next step?
So I used the horizontal equation to find the amount of time, like the time to know how much height it was when it was in 20 feet, when the ball
Okay.
was at 20 feet. So 20 equals t times 34.64. And then I solved for t, and it gave me 0.577 seconds.
We gave you what?
0.577.
Okay.
And then I plugged that into the vertical equation. Negative 16 times 0.577 squared plus 20 times 0.77.
Okay.
And I got 6.2131.
Okay. So what does that mean?
So the ball went over, so C. Yes.
Okay, good. Because the height of the wall is, or the fence is 6 feet, right? Yeah, so it's slightly over. Good. Cool. All right, great. C. Who can else help us out with C? Or let me pause. Any questions up on that? Or anybody get anything different and not sure why? Okay. Can someone help us out with C?
I graphed it. I graphed the x equals 34.6 t.
Okay.
Oh no, wait, I graphed the y. Sorry.
Okay.
And it gave me t as 1.25.
So you when you graphed it, you looked at right here.
Yeah.
Okay.
And then I plugged in t for in the x, so 34.6 times 1.25.
Okay.
And it gave me 43.25 feet.
Okay. You all agree with that? We're good with that? All right, awesome. Very good. So that's the parametric situations lesson. That's how you would apply that. If there are no questions, talk about practice in next class, and then we'll be good. So we just did. I'll put you on mute, for Tammy. Sorry. Okay. We just did these two in one. So that was today. And then tomorrow, so that's a closing out of parametrics. Tomorrow we'll have class tomorrow on Thursday. That'll be on polar. So that'll be at 10 tomorrow. Okay. The practice for this one is posted. It's a worksheet on Google Classroom. All practices are due this Friday at 4:20. Okay. Any last minute questions before we log out?